X is a set with the elements 1, 2, 3, 4, 5, 6, and Y is a set with the elements 1, 3, 5, 7, 9. We have to find X minus Y intersection Y minus X union X minus Y. If we look at the Venn diagram, if this is X and this is Y, then this much is X minus Y and this much is Y minus X. So X minus Y intersection Y minus X is phi. Now if we take phi union X minus Y, then we know that it will be X minus Y only. So the answer will be X minus Y, that is leaving the elements of Y set 1, 3, 5, then 2, 4, 6. This is the answer. Next question. Which of the following is our tautology? Let us make the truth table for PQ. P takes the truth values T, T, F, F. Q takes the truth value T, F, T, F. P imply Q. If P is true, then Q is true. Q imply Q is true. If P is true, Q is F. P imply Q is F. If P is F, Q is true. P imply Q is true. If P is F, Q is F, P imply Q true. So option A is not tautology because all the outcomes are not true. According to the definition of tautology, all the outcomes should be true. Negation P is F, F, T, T. When P is true, negation P is false. When P is true, negation P is false. When P is false, negation P is true. When P is false, negation P is true. Negation P or Q, false, true, true, false, 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 true, 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 false, true. So option B is also not tautology. Now let us find Q imply P. T, 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 F, T, 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 F, 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 T. Now let us find P imply Q and Q imply P. T, 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 F, T, F, T, F, F, T, T, T. Option C is also not tautology because all of them are not true. Now let us find P imply Q imply P. So T, 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 F, F, T, F, T, T. Option D is the tautology because all of them are true. Next question is an algebraic structure dash is called a semigroup. Option A P comma star. Option B Q comma plus comma star. Option C P comma plus. Option D plus comma star. In option D there are two operations. One is plus, other is star. There is no non-empty set. We know that to be a semigroup, any non-empty set A, say, with the binary operation, say not, it should be satisfied with two properties. Number one is closure property, number two is associative property under the binary operation not. But here there is no non-empty set, so option D is not the correct answer. For option A, P comma star, here the binary operation is star and star is not defined, so we cannot say that P is a semigroup under the binary operation star because we cannot say that the two properties closure and associative are satisfied for the elements of the set P under the binary operation star. Here in option B, there are two binary operations, addition and star. Two binary operations are not needed to be a semigroup for a non-empty set Q. So option B is not also correct. Option C is the only one can be a semigroup. The P can be a semigroup under the binary operation addition. As example, we can take P as the set of integers and we know that two properties, the closure and associative, are satisfied for the elements of the set of integers under the binary operation addition. So option C is the correct answer. Next question is, what is the number of edges in a null graph with three vertices? We know the definition of a null graph is that a graph having no edges is called null graph. So the answer is 0. Option A is the correct answer. It does not matter that the null graph contains how many vertices, 3 or more than that or less than that. For a null graph, the number of edges is always 0. Next question is, the statement P and negation P or Q is option A tautology, option B logically equivalent to P and Q, option C logically equivalent to P or Q, option D contradiction. The definition of tautology, we know that all the outcomes should be true. Definition of contradiction, we know that all the outcomes should be false. If we do the truth table for P and negation P or Q, we get 1 true and 3 of them as false. So it cannot be a tautology and contradiction. Now remaining B and C, if we look at P and Q, we see that 1 true and 3 false, which is similar to this. Therefore, option B is the correct answer. Next question. The number of subsets of a set with n elements is, we know by a theorem that the number of subsets of a set with n elements is 2 to the power n. So option B is the correct answer. Next question is incomplete question. Next question is, What is the minimum number of pendant vertices in a tree with 7 vertices? We know the theorem. Any tree with 2 or more vertices contains at least 2 pendant vertices. Therefore, the correct option is C. Next question. Capital X equal the set where the elements are x. X is such that x square equals to 9, comma, twice x equals to 4. The question is x the empty set? Here x is not the empty set because x takes the values plus 3, minus 3 and 2. Next question is, if A and B are subsets of a set X such that Nx is 900, N of A is 300, Nb is 400, N of A intersection B is 130, we have to find N of A union B. We know N of A union B is Na plus Nb minus N of A intersection B. So here Na is 300, Nb is 400 and N of A intersection B is 130. So 700 minus 130 is 570. Next question is, the range of the function f from R to R defined by fx equals to x square if x greater equals to 0, fx equals to twice x plus 3 if x less than 0. We have to find the range of the function. Here, this is set of real numbers. This is also set of real numbers. This is the function f. Say y equals to fx. Then y equals to x square. X equals to plus minus root over y. If we take the set of real numbers, then the negative numbers also will come here and this x will become imaginary. So we cannot take the negative numbers. Therefore, option C is the correct answer, the set of all positive real numbers. Next question, Pn be the statement, Pn n equals to n plus 1, then option A and option B, both of them are correct. We can prove it. Question number 2. Find the inverse Laplace transform of 1 by s plus 2 whole square multiplied by s minus 2. We know inverse Laplace transform of 1 by s square is t. Inverse Laplace transform of 1 by s plus 2 whole square is t e power minus twice t. Inverse Laplace transform of 1 by s minus 2 is e power twice t. Let us take this function as ft and this function as gt. Now, using the convolution theorem, we will have L inverse 1 by s plus 2 whole square multiplied by s minus 2 is f star g, which is equal integration 0 to t f of u g of t minus u du. We have the function ft as t e power minus twice t, so fu equals to u e power minus twice u. 0 to t u e power minus twice u. And we have the function gt as e power twice t. So here we'll have e power twice t minus u du. Now e power twice t is independent of u, so we can take outside of the integration 0 to t u e power minus twice u, and here minus twice u, so minus 4u du. E power twice t. Now let's do the by parts. So first function is u, and e power minus 4u divided by minus 4, and it is from 0 to t. Then ddu of u is 1, so we'll have integration minus integration e power minus 4u by minus 4 du. E power twice t, putting the values of u as t, so we'll have t e power minus 4 t by minus 4, and while putting u equals to 0 we are getting the term as 0, then minus and this minus plus, and e power minus 4u by 16 minus 16 0 to t. So this is e power twice t, and t e power minus 4t by minus 4, and then minus e power minus 4t by 16, and minus minus plus e power 0 is 1, 1 by 16. So if we take 1 by 16 common, then we'll have 1 minus 4t e power minus 4t minus e power minus 4t e power twice t. We can write by this way also, 1 by 16 e power twice t minus 4t e power twice t, that is minus e power minus twice t. So this is the answer. Question number 3, we have to find the inverse Laplace transform of thrice s divided by 4a square plus 16. We know inverse Laplace transform of s by s square plus 4 square is cos 4t. Using change of scale property, inverse Laplace transform of twice s by twice s whole square plus 4 square will be half cos 4 t by 2, that is half cos twice t. Now if we take 2/3 of inverse Laplace transform of thrice s by 4s square plus 16, then we will have half cos twice t. Because we are taking here 3 here to make it like in the question given, so 1/3 and 3 will be cancelled. The 2 will go inside. So this is equals to half cos twice t. So if we write here 2 by 3 and inside it is 3s, then it is similar to the previous line. So inverse Laplace transform of thrice s by 4s square plus 16 is 3 by 4 cos twice t. This is the answer. Question number 4. Solve d2 minus 1y equal a cos hyperbolic nt, where y at 0 equals 0, y prime at 0 equal 2. Let's start the solution. Let us take Laplace transform both sides of this equation. Then we'll have Laplace transform of y double prime minus Laplace transform of y equal a Laplace transform of cos hyperbolic nt. If we take Laplace transform of y as fs, then by the theorem that the Laplace transform on second order derivative is a square fs minus s f at 0 minus y prime 0, and here L of y, Laplace transform of y is fs. In right hand side, a multiplied by the Laplace transform of cos hyperbolic nt is s by s square minus n square. Now in the question it is given that y at 0 is 0, y prime at 0 is 2. So let us put these values in this equation. Then we'll have s square fs, this term is 0 and this term is 2, and this is fs equal a s by s square minus n square. Let us take fs common, then s square minus 1 fs is a s by s square minus n square plus 2. So fs is a s by s square minus n square s square minus 1 plus 2 by s square minus 1. Now let us find this s by s square minus n square and s square minus 1 in partial fraction. So let us take s by s square minus n square s square minus 1 as as plus b by s square minus n square plus cs plus d by s square minus 1. So s equals to as plus b multiplied by s square minus 1 plus cs plus d multiplied by s square minus n square. Now let us take s as 1. So we'll have this term as 0 and here c plus d, and here s is 1, so 1 minus n square, right hand side 1. So c plus d is 1 by 1 minus n square. Now let us put s equals to minus 1, then we'll have here minus c plus d. So minus c plus d, rest of the terms are same, 1 by 1 minus n square. Now if we do the simplification with these two equations, then we'll have, say this equation is as 1 and this equation is 2. From 1 and 2 we get minus c plus c cancel, twice d is, there should be a minus sign here because s equals to minus 1, so in the left hand side there is a minus sign. So if we add them, minus c plus c cancel, twice d, and right hand side this and that term will be cancelled. So d equals to 0. And putting d 0, we'll have c equals to 1 by 1 minus n square. Or we can write as minus 1 by n square minus 1. Now let us take s as n. Then this part is 0 and here we will get n square minus 1 and an plus b, left hand side this is n. So we'll have n equals to an plus b and n square minus 1. So an plus b equals to n by n square minus 1. Now if we take s as minus n, then we'll have the same here, just this will be minus an plus b minus an plus b equal minus n by n square minus 1. Now say this line is 4 and this equation is 5. So from equation 4 and 5 we get, look, if we add them, an minus an will be cancelled and twice b and right hand side cancel, so b equals to 0. And um, putting b as 0, we are getting an as n by n square minus 1. N will be cancelled, so a equal 1 by n square minus 1. Now let us put all of these values here. A term and c term, because b and d both of them are 0. Now we'll have s by s square minus n square and s square minus 1, which is equal as plus b by s square minus n square plus cs plus d by s square minus 1. A is 1 by n square minus 1 and this is s by s square minus n square plus c is minus 1 by n square minus 1 and d is 0, so this is s by s square minus 1. Now what is fs? Fs equals to as by, so there will be a term a and by n square minus 1 and this is s by s square minus n square and here it is minus a by n square minus 1 s by s square minus 1 and plus 2 by s square minus 1. So fs is what? Fs is Laplace transform of ft. So this is actually Laplace transform of ft. So yt. So yt is what? Yt is a by n square minus 1 inverse Laplace transform of s by s square minus n square minus a by n square minus 1 inverse Laplace transform of s by s square minus 1. plus twice inverse Laplace transform of 1 by a square minus 1. Now this is a by n square minus 1. An inverse Laplace transform of s by a square minus n square is cos hyperbolic nt by n minus a by n square minus 1. Inverse Laplace transform of s by a square minus 1 is cos hyperbolic t plus twice inverse Laplace transform of 1 by a square minus 1 is sine hyperbolic t. Now we can arrange it. Yt is a by n square minus 1 taken common. Then we will have cos hyperbolic nt by n minus cos hyperbolic t plus 2 sine hyperbolic t. This is the required solution. Question number 5. The center ZG of a group G is a normal subgroup of G. We know the definition of ZG, which is A belongs to G colon AG equals to GA for all G belongs to G. And we know that ZG is a subgroup of G. So for any G belongs to G and any A belongs to ZG, GAG inverse equal AGG inverse equal AE, which is equal A, and A belongs to ZG. Therefore, G belongs to G, A belongs to ZG imply GAG inverse belongs to ZG. Hence, ZG is a normal subgroup of G. Question number 6. If xz equal twice z square plus 5z plus 14 divided by z minus 1 power 4 be generating function of the sequence xn n from 0 to infinity, then find x0, x1, x2 and x3. Let's start. We can write this 2z square plus 5z plus 14 multiplied by 1 minus z power minus 4. Now we know from the expansion of this 1 minus z power minus 4 as 1 plus 4z plus 10z square plus 20z cube plus 35z to the power 4 plus so on. Now to remember this 1 minus z power minus 4, you can remember this formula 1 minus z power minus n as 1 minus nz plus n into n minus 1 by factorial 2 z square minus n into n minus 1 n minus 2 by factorial 3 z cube plus so on. So put the value of n as 4, you will get the desired series. You look that we have to find x0, x1, x2 and x3. So we will not go beyond z cube. If we get more than z cube, we will discard that. Let us first multiply with 14 because here the power of z is 0. So we will have 14 plus 14 into 4, 56z plus 14 into 10, 140 z square plus 280 z cube, and we'll discard rest of the terms. Next with 5z. So here plus 5z and then 20 z square and then 50 z cube and so on. Next with 2z square, so plus 2z square, then 20 z cube and so on. So if we add them, then we are getting 14 plus 61 z plus 182 z square plus 338 z cube plus so on. Now if we compare with this the sequence, then we'll have here the x0 as 14, x1 as 61, x2 as 182 and x3 as 338. Question number 7a. Prove by mathematical induction that 6 power n plus 2 plus 7 power twice n plus 1 is divisible by 43 for each positive integer n. Say Pn is the statement that 6 power n plus 2 plus 7 power twice n plus 1 is divisible by 43. Now let's take n equals to 1. Then P1 is 6 power 1 plus 2 plus 7 power 2 plus 1. So that is 6 cube plus 7 cube. Now if we apply a plus b whole cube minus thrice ab into a plus b, then we will have 6 plus 7 whole cube minus thrice into 6 into 7 into 6 plus 7. So it is 13 cube minus 3 into 6 into 7 and inside it is 13. So if we take 13 common, then inside 13 square, that is 169 minus here 18 into 7, that is 126. So it is 13 into 43. Therefore P1 is divisible by 43. Now we have to prove it for n equals to k. Let's take n equals to k. Then pk becomes 6 power k plus 2 plus 7 power twice k plus 1. This is equal 6 power k into 6 square plus 7 power twice k into 7. Now this is 6 power k into 36 plus this can be written as 7 square power k into 7. So this is 6 power k into 36 plus this is 49 power k into 7. This is 6 power k into 36 plus this one 49 can be written as 43 minus plus 6 power k into 7. 6 power k into 36 plus this can be written as in binomial expansion. So we can write that NC0 is 1, 6 power k 43 power 0 that is 1 plus NC1 that is KC1 that is k 7 is there, 7 into 6 power k 6 power k minus 1 into 43 plus k into k minus 1 by factorial 2 6 power k minus 2 43 square plus so on. Now look from these two terms you can take 6 power k common, then you will have 36 plus 7, and here you look that you can take 43 common. So if you take 43 common, then there is k into 6 power k minus 1 plus k into k minus 1 by factorial 2 6 power k minus 2 into 43 plus so on. Now this is 6 power k into 43 plus 43 into the whole term. Now look, both the terms contain 43, therefore pk is divisible by 43. Here we forgot to write one 7. This 7 is multiplied 7 into with all of these terms. So 7 into here 7 into. The result is same, pk is divisible by 43. Now we have to show that pk plus 1 is true. pk plus 1 is 6 to the power k plus 1 plus 2 plus 7 to the power twice k plus 1 plus 1, which is 6 to the power k plus 3 plus 7 to the power 2k plus 3. We can write it as 6 power k into 6 power cube plus 7 power twice k into 7 power cube. 6 power k 6 power cube plus 7 power twice k can be written as 49 power k into 7 cube. 6 power k into 6 power 3 plus 49 can be written as 46 plus 6 power k into 7 cube. Let us expand it. Six power k, sorry, this one should be 43. 6 power k plus k 6 power k minus 1 43 plus k into k minus 1 by factorial 2, 6 power k minus 2, 43 square plus so on. Now here it was 1 7 power 3. So now from these two terms 6 power k can be taken common, then inside it is 6 cube plus 7 cube. And from rest of the terms we can take 43 common, then we'll have k 6 power k minus 1 plus k into k minus 1 by factorial 2, 6 power k minus 2 into 43 plus so on. Now look, the first term, this is P1. P1 is 6 cube plus 7 cube, and we have proved that P1 is true. And in the next term, 143 is multiplied. Here also 1 with this term 7 cube multiplied. Okay, so there should be 7 cube into 43. Therefore, pk plus 1 is true. Then pk plus 1 is divisible by 43. Hence, we can say Pn is true. So, Pn is also divisible by 43. Question 7b. Using set theory, find the LCM and HCF of 48, 72, 24. Let's start. 48 is 2 multiplied 2 multiplied 2 multiplied 2 multiplied 3. 72, 2 multiplied 2 multiplied 2 multiplied 3 multiplied 3. 24, 2 multiplied 2 multiplied 2 multiplied 3. Now if we draw the Venn diagram, set A, set B, set C. This is A union B union C, which is actually LCM of ABC. Set A, set B, set C. This part is A intersection B intersection C, which is ACF of ABC. Here the set A contains the elements 2, 2, 2, 2, 3. Set B contains the elements 2, 2, 2, 3, 3. Set C contains 2, 2, 2, 3. Now A union B union C is 2, 2, 2, 2, 2, 3, 3. That is 144. This is the LCM. And A intersection B intersection C is 2, 2, 2, 3. So 24. This is the HCF. Question 8a. Let G be a group and A belongs to G. Prove that the mapping FA G to G defined by FAX equal AX for all X belongs to G is a bisection. Bijection mapping means 1 to 1 and onto. If we are able to show that FA is invertible, then we can conclude that FA is bijective mapping. Here it is given that FAX equals to AX. So FA inverse FAX is FA inverse AX. And this is A inverse AX. And which is A inverse AX. So that is X only. Next FA inverse X. FA A inverse X. A inverse X. A inverse X. That is X. Therefore, FA inverse FAX is equal FA inverse X, which implies FA is invertible. It implies FA is 1 to 1 and onto. Hence, FA is bijective. Question 8b. Give an example of an abelian group which is not cyclic. Here, 3 examples are given. Any one you can write. First example, set of real numbers. Second example, set of rational numbers. Both of them are abelian group and they are not cyclic. Example 3, Klein's 4 group. It is also abelian group but not cyclic. Here first 2 examples are of infinite group and Klein's 4 group is finite group. The set of real numbers and set of rational numbers, both of them are abelian group which are not cyclic under the binary operation addition. Klein's 4 group has been discussed in details in another video lecture. If you are interested, you may watch that. The link has been given below in the description. Question 8c. Find the generators of the group Z8, binary operation addition here. For any k belongs to Z8, GCD of K8 is 1 if and only if K equals to 1, 3, 5, 7. Therefore, there are 4 generators. Did it. Question 8d. Let H be a subgroup of a group G. Define a relation rho on G by A rho B if and only if A inverse B belongs to H. Prove that rho is an equivalence relation on G. Also prove that for A belongs to G, the equivalence relation class of A is the left coset AH. What is the definition of equivalence relation? Rho is an equivalence relation of G if rho satisfies the following for all A, B, C belongs to G. Number 1, A rho A, that is called reflexive. Number 2, if A rho B, then B rho A, which is called symmetric. If A rho B and B rho C, then A rho C, which is called transitive. Now we will show each of them one by one. Here there should be one R. A rho A, both A implies A inverse A, which is actually E, and H is a subgroup of group G, therefore E belongs to H. Hence, rho is reflexive. Next, A rho B, both A implies A inverse B, both A implies A inverse B inverse equal B inverse A inverse inverse, that is B inverse A, which implies B rho A. Therefore, the relation rho is symmetric. Now let's take A, B, C belongs to G. Then A rho B, both A implies A inverse B belongs to H. B rho C, both A implies B inverse C belongs to H. Now let us multiply both of these, A inverse B, B inverse C. Then we will have A inverse B, B inverse C. B inverse is E, so we can write A inverse C, which will imply A rho C. Therefore, rho is transitive. Now we have to prove the second part of the question. Also prove that for A belongs to G, the equivalence class of A is the left coset AH. It is given that A inverse B belongs to H. Then we can write A inverse B H equal H. How? If H small h belongs to capital H, which will imply small h equal capital H. Why? Because H is the subgroup of G. We know a theorem. If H is any subgroup of a group G and H belongs to H, then HH equals to H equals to HH. Now here we can take A in left hand side, A inverse B H A H. A will be there in left of H in the right hand side. Now A inverse B H is A H. A inverse is E, which belongs to H, EBH. So BH equal AH. Therefore, the equivalence class of A is the left coset, AH. Question 9A1. Solve the following recurrence relations by substitution. An equal an minus 1 plus n square, n greater equals to 1, where a naught equals to 7. An equal an minus 1 plus n square. Replacing n by n minus 1, n minus 2, n minus 3, say 4, 3, 2, 1. So here a n minus 1 is a n minus 2 plus n minus 1 square. A n minus 2 equal a n minus 3 plus n minus 2 square. A n minus 3 equal a n minus 4 plus n minus 3 whole square. A 4 equal a 3 plus 4 square. A 3 equal a 2 plus 3 square. A 2 equal a 1 plus 2 square. A 1 equals to a naught plus 1 square. Now if we add all of them, then in left hand side and right hand side these terms will be cancelled. In this way, at the end we will have an equal a naught plus 1 square plus 2 square plus 3 square up to n square. A naught is 7 given, therefore an equal 7 plus the sum of the square of n natural numbers is n into n plus 1 twice n plus 1 by 6. So this is the required answer. Next, question 9A2. Solve the following recurrence relations by substitution. An equal an minus 1 plus twice n plus 1, where a naught equals to 1. Like the previous sum, we will replace n by n minus 1 and so on. Then we will have a n minus 1 equal a n minus 2 plus twice n minus 1 plus 1. Then a n minus 2 equal a n minus 3 plus twice n minus 2 plus 1. And a3 say a2 plus 2 into 3 plus 1. A2 equal a1 plus 2 into 2 plus 1. A1 equal A0 plus 2 into 1 plus 1. Now if we add all of them, then similarly like the previous sum, these terms will be cancelled in both sides. Then we'll have An equal A0 plus twice 1 plus 2 plus 3 up to n, plus there are n numbers of what, so n. A0 is 1 given plus 2, 1 plus 2 plus 3 plus n, sum of n natural numbers, n into n plus 1 by 2 plus n. Here 2 to cancelled. Then we'll have n square plus n plus n twice n plus 1. So this is n plus 1 whole square. This is the required answer. Question 9b1. Solve the following recurrence relations together with the given initial conditions. N equals to an minus 1 plus twice an minus 2, n greater equals to 2, where a0 equals to 0, a1 equals to 1. This recurrence relation can be written as, say, x square minus x minus 2 equal 0. So this is x plus 1, x minus 2 equal 0. X equal minus 1, 2. The general solution can be written as an equal a minus 1 power n plus b 2 power n. Now let us put n equals to 0. Then we will have a0 equal a plus b. So a plus b equals 0 because a0 is 0 given. Putting n equals to 1, a1 equal minus a plus twice b. a1 is 1 given, so minus a plus twice b equal 1. We have a plus b equals 0, a plus b equals 0. If we solve, cancel, thrice b equal 1, b equal 1/3. So a equal minus 1/3. Now we can write an as minus 1/3 minus 1 power n plus 1/3 2 power n. This is the required solution. Question 9b2. Solve the following recurrence relations together with the given initial conditions. An minus 8, an minus 1 plus 16, an minus 2 equals 0 for n greater equals 2, where a2 equals 16, a3 equals 80. The given recurrence relation can be written as x square minus 8x plus 16 equals 0. So this is x minus 4 whole square equal 0. X equal 4 comma 4. The general solution can be written as an equal a plus b n 4 power n. Now putting n equals to 2 because here a2 is given. So we have a2 equal a plus twice b 4 square, that is 16. a2 is given as 16, so 16 equals 16 a plus twice b. So a plus twice b equal 1. Now let us put n equals 3 because a3 is given. So we have a3 equal a plus thrice b 4 power 3. a3 is given as 80 equal a plus 3b, and 4 cube is 64. Now we can cancel here. 5 equal 4, A plus 12B. Now A plus twice B equal 1, so we can multiply with 4. Then we will have 4 equal 4A plus 8B. So 1 equal, this is cancelled, 4B. B equal 1 by 4. If we put here B as 1 by 4, then A plus half equal 1. So A equal half. Then the solution becomes AN equal half plus 1 by 4 n 4 power n. We can take half common outside. Then we'll have 1 plus n by 2 4 power n. This is the required answer. Question 10a. A relation rho on the set N is given by rho equal AB belongs to N, where A divides B. Examine if rho is number 1 reflexive, number 2 symmetric, number 3 transitive. Let us take A comma A belongs to N. A divides A. Therefore, A comma A belongs to rho. Hence, rho is reflexive. Next, let us take A comma B belongs to N. A divides B. It does not imply that B divides A. Let us take one example. Say 2 comma 4. It belongs to N. 2 divides 4. But 4 does not divide 2. Therefore, rho is not symmetric. Now let us take A comma B belongs to N and B comma C belongs to N. Then A divides B and B divides C, which imply A divides C. Here AB belongs to rho, BC belongs to rho, which imply AC belongs to rho. Therefore, rho is transitive. Question 10b. A relation rho is defined on the set Z by A rho B if and only if AB greater than 0 for A comma B belongs to Z. Examine if rho is reflexive, symmetric, transitive. Let A belongs to Z. Then A into A greater than 0 because it is given AB greater than 0. So A rho A holds for all A belongs to Z. Therefore, rho is reflexive. Now let A B belongs to Z and A rho B. Then AB greater than 0, which imply BA greater than 0, which imply B rho A. Therefore, rho is symmetric. Now let A, B, C belongs to Z such that A, B, C greater than 0. Now A rho B, B rho C. We have to show that A rho C. For A row B, AB greater than 0. For B row C, BC greater than 0. Now AB into BC greater than 0. So which imply A, C, B square greater than 0. B square not equals to 0. Then AC greater than 0. Therefore A row C. If we take A equals to 1, B equals to 0, C equals to minus 3, then AB equals to 0, 1 into 0. BC equals to 0. But AC equal 1 into minus 3, which is minus 3 less than 0. So therefore, AB greater than 0, BC greater than 0 do not imply AC greater than 0. Therefore, rho is not transitive. Question number 11a. Solve the following equation using generating function an minus 5 an minus 1 plus 6 an minus 2 equals 0, where n greater equals to 2 with the boundary condition a0 equal 1, a1 equal 1. This is of 8 marks question. So we have to complete it approximately within 20 minutes. Let's start. Let us take the generating function gx for the sequence an as summation n equals to 0 to infinity an x power n, which is we can write as infinite series a0 plus a1x plus a2x square plus a3x cube plus so on. Now the given equation is an minus 5 an minus 1 plus 6 an minus 2 equal 0. Let us take this equation as 1. Now multiply equation 1 by x to the power n and summing up from 2 to infinity. Sum n equals to 2 to infinity an x to the power n minus sum n equals to 2 to infinity 5 an minus 1 x to the power n plus sum n equals to 2 to infinity 6 an minus 2 x to the power n equals to 0. Now you look here that okay, let's write again. Gx is a0 plus a1x plus a2x square plus a3x cube plus so on. Now we can write gx minus a0 minus a1x equal a2x square plus a3x cube plus so on. Right hand side can be written as summation n equals to 2 to infinity an x power n. So let us substitute the value of this here. Similarly, we can find for an minus 1 x power n and for an minus 2 x power n. Let us find for n minus 1 x power n. Gx equals to a0 plus a1x plus a2x square plus a3x cube plus so on. Summation n equals to 2 to infinity a n minus 1 x power n. There is nothing here, so we can write here x to the power 0 sum n equals to 2 to infinity a n minus 1 x power n. X to the power 0 can be written as x power 1 minus 1 sum n equals to 2 to infinity a n minus 1 x power n. Now let us keep x outside and take x power minus 1 inside. Then we will have n minus 1 x power n minus 1. Now you see that if you put n equals to 2 here, then we are getting x a1 x power 1 plus a2 x power 2 plus a3 x power 3 plus so on. Now you look here that this part is what? That is gx minus a0. a1x plus a2 x square plus a cube x cube plus so on. Therefore, we can substitute this value here that it is nothing but x gx minus a naught. Now let us find the third term a n minus 2 x power n. Sum n equals to 2 to infinity a n minus 2 x to the power n. There is nothing, we can take it as x to the power 0 sum n equals to 2 to infinity a n minus 2 x power n. X to the power 0 can be written as x2 minus 2 sum n minus 2 to infinity a n minus 2 x power n. Now x2 outside and x minus 2 taking inside, a n minus 2 x power n minus 2. Now this is the series a0 x to the power 0 plus a1 x to the power 1 plus a2 x square plus a3 x3 plus so on. This is nothing but the generating function gx. So we can substitute the value of this term as x square gx. Now let us substitute all of these values here. Then we will get gx minus a naught minus a1x minus this one 5 common and inside gx minus 5x a naught and here 6x square gx equal 0. Now let us take gx common and put the values of a0 and a1. Then we'll get the equation as gx equal 1 minus 4x divided by 6x square minus 5x plus 1. If we do the middle term factorization, then we'll have 1 minus 2x, 1 minus 3x. Now let us do the partial fraction 1 minus 4x by 1 minus 2x, 1 minus 3x as a by 1 minus 2x plus b by 1 minus 3x. Then 1 minus 4x is a of 1 minus 3x plus b of 1 minus twice x. Now let us take x as 0, then we'll have 1 equals to a plus b. Now let us take x equals to 1, then we'll have minus 3 equals to minus 2a and here minus b. Now if we do the simplification, then minus a equal minus 2. So a equal 2. Now put a equals to 2 here and you will get b as minus 1. Then gx is a, that is 2, 2 by 1 minus 2x and b is minus 1. So minus 1 by 1 minus 3x. Now let us take this 2 here and then it is 1 by 1 minus 2x minus 1 by 1 minus 3x. So 2 into 1 minus 2x power minus 1 minus 1 minus 3x power minus 1. So we can write 2 into summation 2 to the power n x to the power n equals to 0 to infinity minus sum n equals to 0 to infinity 3 to the power n x to the power n. This is the required solution.